Financial markets don't just move randomly. They evolve. And sometimes, that evolution follows a hidden geometric pattern long before the crash hits. We're talking about topology. But extracting those patterns at scale is computationally brutal. Enter quantum computing. Today, we're diving into a cutting-edge adaptation of Pauli Correlation Encoding for quantum topological data analysis, and how it's being used to estimate Betti numbers from S and P500 returns. This isn't just theory. It's a full pipeline, tested against real market data, with results that reveal both the promise and the hard limits of near-term quantum machine learning. Let's start with why we're looking at topology at all. Traditional volatility measures like variance or value at risk look at point-wise statistics. They miss the big picture. But when markets approach a crisis, the underlying dynamical attractor undergoes a structural deformation. Topological Data Analysis, or TDA, captures this by treating financial time series as point clouds in a high-dimensional space. We use a Taken's delay embedding to reconstruct the attractor from a single index, like the S and P500. Then we build a Vietoris-Rips complex, which connects points based on a distance threshold. The key invariant here is the Betti number. Specifically, the first Betti number, beta 1, counts the number of one-dimensional loops in the data manifold. In financial contexts, a sustained rise in beta 1 has been shown to precede major crashes by hundreds of trading days. It's a leading indicator of systemic stress that purely local statistics completely miss. So how do we actually compute these Betti numbers? Mathematically, beta k equals the dimension of the null space of the kth combinatorial Laplacian. To find it, you have to construct and diagonalize this matrix. The problem? The Laplacian dimension grows combinatorially with the number of simplices. Classically, dense diagonalization scales as O of nk cubed. For real-time market monitoring across sliding windows, that quickly becomes prohibitive. Quantum algorithms were proposed to solve this. The seminal LGZ algorithm uses quantum phase estimation on the unitary exponential of the Laplacian. By measuring the phase corresponding to zero eigenvalues, you can estimate the Betti number. But standard QPE is brutal for near-term hardware. It requires deep circuits, many ancilla qubits, and recent complexity theoretic analyses show that superpolynomial quantum advantage actually requires exponentially large Betti numbers and very specific spectral gap conditions. So while QPE is theoretically elegant, it's practically out of reach for NISQ devices. This is where the new work steps in. The researchers adapted a framework called Pauli Correlation Encoding, or PCE, to the spectral problem of Betti number estimation. PCE was originally designed for combinatorial optimization. It compresses M classical binary variables into n qubits using k-body Pauli correlators. The magic is in the qubit compression. You can encode O of nk variables into roughly nk to the power of 1 over kappa qubits. For quadratic encoding, that's a square root savings. For cubic, it's a cube root. But here's the twist. Canonical PCE decodes variables by taking the sign of the Pauli expectation. This work does something fundamentally different. They treat the continuous expectation values of the Pauli strings as the actual eigenvector coefficients. Instead of binary outputs, you get a continuous vector between -1 and +1. This vector parameterizes a trial state in the simplex space, and you evaluate a Rayleigh quotient classically. The loss function becomes the ratio of the quadratic form C transpose delta C over the norm squared of C. Minimizing this gives you the smallest eigenvalue accessible to your ansatz. If it drops below a threshold, you found an approximate null vector. Finding one null vector isn't enough. You need to count them to get the Betti number. They use variational deflation. Once you find the first approximate null vector, you add a penalty term to the loss function that penalizes overlap with already found vectors. You repeat this sequentially. Each successful minimization below the threshold increments your Betti estimate. Now here's a critical technical detail. The original PCE framework has a formal proof that its gradient variance is lower bounded by a superpolynomial function of n, which mitigates barren plateaus. But that proof only applies to bilinear loss functions. Your Rayleigh quotient is rational in the correlators because of the denominator, and your deflation penalty adds ratio terms. So the formal trainability guarantee does not transfer. The authors don't claim a proof here. Instead, they run an empirical gradient variance analysis across 4 to 12 qubits. The results? The variance decays only polynomially, roughly as 1 over n. The log-log slope is around -1. That's a far cry from the exponential vanishing that defines a barren plateau. It's strong empirical evidence that this encoding remains trainable, even if the math doesn't quite cover it yet. Let's talk about what actually happens when you run this. On 6 synthetic toy Laplacians, the pipeline recovers the exact Betti numbers perfectly. The loss converges to machine precision for null vectors and jumps when no more exist. But then they test it on the actual S and P500 Laplacians, where beta 1 ranges from 1 to 22. Here, the random start optimizer hits a wall. No matter the Betti number, the minimum loss stalls around 1.2 to 1.8. It never finds a null vector. Is the encoding broken? No. When they run a fully expressive state, the correlators actually reach the true null vectors with near-perfect overlap. The problem is purely the optimization landscape of the hardware-efficient ansatz. The tiny spectral gap of the Laplacian traps the optimizer. The fix: classical warm starting. They take the classical null space surrogate, project it into the quantum parameter space, and use it as an initial point. Suddenly, the optimizer converges to machine zero loss and recovers beta 1 exactly across every scale. This isolates the bottleneck. It's the landscape, not the encoding or the qubit count. They also test whether beta 1 actually predicts crashes. Using a chronological split, training on 2003 to 2006, and testing on 2007 to 2010, the beta 1 classifier achieves a test ROC AUC of 0.818. That's significantly better than a standard volatility proxy. But here's the catch that matters for real deployment. When they test out of distribution on the 2020 COVID shock and the 2022 rate hike cycle, the classifier fails. The AUC drops to near zero for COVID and chance level for 2022. This isn't a bug. It's a feature. The 2008 crisis was a slow buildup of correlated stress that topology tracks well. The 2020 shock was a fast, exogenous dislocation with a completely different return series topology. A single fixed threshold beta 1 classifier isn't universal. It's regime-specific. Any practical deployment would need regime-aware calibration. From a hardware perspective, PCE trades qubits for depth. LGZ uses O of log nk qubits, but needs exponentially deep circuits and ancillas. PCE uses O of nk to the 1 over kappa qubits, but runs on shallow ancilla-free circuits. For near-term devices where depth is the binding constraint, that's a massive advantage. Resource extrapolations suggest a classical crossover around nk greater than 10,000, where O of nk cubed diagonalization finally overtakes the projected quantum cost. But that's a research target, not a demonstrated capability. So what's next? The big open question is finding a quantum-native warm start. Right now, we're using classical null space guidance to bypass the landscape trap. A fully independent quantum pipeline would need a problem-informed or adaptive ansatz that can navigate to the null space without classical help. There's also work to be done on subspace search methods to handle higher multiplicity null spaces more efficiently, and formal expressivity proofs for this continuous PCE loss. This work doesn't claim quantum advantage at the scales tested. At the dimensions evaluated, classical methods solve each window in under 200 milliseconds. But it does deliver a complete, depth-efficient blueprint for quantum TDA. It proves that Pauli correlation encoding can be adapted to eigenvalue counting, that the optimization landscape is the true bottleneck, and that topological features carry regime-dependent predictive power in financial markets. The path forward is clear. Refine the ansatz, eliminate the classical warm start, and push this onto real hardware. If you want to dive into the code, verify the results, or run the pipeline yourself, everything is open source. The intersection of topology, quantum optimization, and financial physics is moving fast. Stay curious, keep experimenting, and I'll see you in the next one.